Hello guys, welcome to a new video. In this video, we are going to discuss about particular integral. Before studying about particular integral, let us first look at its definition. A particular integral is a specific solution to a non-homogeneous linear differential equation. The general solution basically combines the complementary function, that is CF, and the particular integral PI. In this video, we are only concentrating on how the four cases of PI and how to work with these four cases. In these four cases, the RHS keeps on varying. RHS mainly takes four different forms. The first form is where the RHS takes the exponential function, that is, it is of the form e to the power ax. The second form is where RHS takes sin ax or cos ax form, that is, it takes trigonometric values. The third case is where RHS is of the form x raised to n, that is a polynomial function. Here n is nothing but a positive integer. And the fourth case is where RHS is a combination of our first case and any other two cases, that is case 2 or case 3. That is case 2 or case 3. That is, the fourth case is denoted by the RHS is denoted by e to the power ax into v, where we can take either case 2 or case 3. That is, we can take sin ax, cos ax, or x to the power n. So our first case is nothing but the exponential function. In this case, the RHS of the equation is an exponential function in this form. This is the general formula for this case. The RHS is nothing but e to the power ax. Now coming on into how to find the PI. This is our working methodology. That is, we take 1 by the function with a substituted with respect to d in the equation in the denominator, multiplied by e to the power ax in the numerator. If f of a, that is while substituting a in the given function, is not equal to 0. If it is equal to 0, we take the derivative of the same and then substitute a in it and then do the same. Now going on to our first example. This example, the given solution is d minus 3 into y is equal to e to the power 2x. Here, let's first identify what a is. A is nothing but 2. Now, going on how to solve the equation, let's first look at the LHS of the given equation, that is d minus 3. Now, substituting 2, that is a, in this given equation, we get 2 minus 3, that is equal to minus 1. As noted here, we see that this is not equal to 0. Therefore, the PI can be easily written as e to the power 2x divided by 1 of f of a. F of a here is nothing but minus 1. That helps us arrive at the final answer, that is e to the power 2x by minus 1, which is nothing but minus of e to the power 2x. Let us look at a second example for our case 1, that is where the RHS is equal to e to the power ax. Now here the given equation is not of the form where we see the differential operator, that is d. So our first task here is to convert this LHS into our operator form, that is nothing but d square minus 2d plus 10 into y is equal to e to the power 2x. From this equation, we can find what f of d and what e to the power 2x is. So here f of d is nothing but d to the power 2 minus 2d plus 10, and a is nothing but 2. So now substituting 2 in this f of d, we find that 2 square minus 2 into 2 plus 10, that is 4 minus 4 plus 10, that is nothing but 10. This is not equal to 0. Therefore, we can directly divide our RHS with this equation, with this this equation substituted with a. Therefore, our PI is nothing but e to the power 2x divided by 10. So now let us look at the case 2. Case 2 is of the form where RHS is equal to sin ax or cos ax. That is, the general equation is nothing but f of d is equal to sin ax or cos ax, that is this. Here our working methodology is that we substitute d square is equal to minus of a square and then calculate. That is, we have a general formula, that is pi is equal to sine of ax or cos of ax divided by f with the substitution of d square is equal to minus of a square. Now coming into our first example. Here the given equation is d square plus 5 into y is equal to sine 2x. From this we can identify that a is equal to 2. That implies minus of a square is equal to minus of 4. Now we know the general formula, that we just substitute this minus 4 in this general formula, which is this equation, f of d equation. That is, we get pi is equal to sine 2x divided by minus 4, which is substitution for d square, plus 5. That is, minus 4 plus 5 is nothing but 1. Therefore, our pi is equal to sine 2x. Here we are looking at a second example for the second case, that is where the RHS is either of the form cos ax or sin ax. Here the RHS is cos square x. So first let us simplify this RHS. While simplifying cos square x, we know that cos square is equal to nothing but 1 plus cos 2x divided by 2. This can be written in the form 1 by 2 into e to the power 0x plus cos 2x by 2. Now coming into how to find the pi for this question. Here we split our pi into two parts, that is part 1 and part 2. Part 1 we consider 1 by 2 into e to the power 0x. Here e to the power 0x is nothing but 1, and second part we consider cos 2x divided by 2. Now going into our part 1. Here 1 by 2 into e to the power 0x divided by f of d. We know f of d is nothing but d square plus 2d plus 1. Now here from this equation we can identify a is equal to 0. Therefore substituting 0 in f of d, we get 0 plus 0 plus 1, which is nothing but 1. And e to the power 0x is nothing but 1. Therefore pi 1 is equal to 1 by 2. So now looking at the second part for this question, we are considering cos 2x by 2. 1 by f of d into cos 2x by 2. Here the RHS is of the form cos 2x. Therefore we have to apply case 2 here. Now considering f of d, that is d square plus 2d plus 1. We know in case 2 we substitute d square is equal to minus of a square. Here minus of a square is equal to minus of 2 square, which is equal to minus 4. Now while substituting minus 4 in this f of d, we get minus 2 square plus 2d plus 1, that is 2d minus 3. Then we have to multiply both the numerator and denominator with the conjugate of 2d plus 3, that is 2d minus 3, that is 2d plus 3. After multiplication, this is, we get it in the form 2d plus 3 into cos 2x divided by 2 into 4d square minus 9. 4d square minus 9 can be simplified like 4 into minus 4 minus 9. Here we are substituting d square is equal to minus 4, that is minus 8 minus 9, that is minus 16 minus 9, that is minus of 25. Minus of 25. Minus 25 into 2 is equal to minus 1 by 50, and our numerator is 2d plus 3 into cos 2x. Multiplying 2d plus 3 with cos 2x, we get 2d into cos 2x plus 3 cos 2x. Now using this differentiation operator, we take the derivative of cos 2x, which is minus 2 into sin 2x, that is minus 4 sin 2x plus 3 cos 2x into minus 1 by 50 is our final answer. Okay, now let us look at case 3. Here the RHS is nothing but x to the power n form, where n is a positive integer. Here the pi is found using the general formula x to the power n divided by f of d, where f of d is converted into phi of d formula, and then this is taken to the numerator that is 1 plus phi of d whole raised to minus 1 into x to the power n. Now let us look at the working methodology. First step is to take the lowest degree term common from f of d to get an expression of the form 1 plus or minus phi of d in the denominator, and then we take it to the numerator to make it in the form 1 plus or minus phi of d whole to the power minus 1. Then this equation is expanded using binomial theorem up to nth degree. Then we simplify it using the derivative operator. That is, we consider d is nothing but the first derivative, d square is nothing but the second derivative, and d cube is nothing but third derivative, and so on it goes. Looking at the first example, the given equation, that is d to the power 2y by dx square minus y is equal to 5x minus 2. Here the RHS is 5x minus 2 and our LHS is not in our general formula using derivative operator. So we have to first convert it into our general formula, that is d square minus 1. Now coming on how to find pi, 1 by d square minus 1 into 5x minus 2. We convert that into this form by multiplying by minus 1, that is minus of 1 minus d square. Now taking that to the numerator, this minus 1 is multiplied here to make it into our general formula 1 plus or minus phi of d. Now take it into our numerator, we get this formula with minus of 1 minus d square whole to the power minus 1 into 5x minus 2. Here we expand this using binomial theorem. We get 1 plus d square plus d raised to 4. Multiplying that with 5x minus 2. Using the operators, we get 5x minus 2 plus 0. That is nothing but minus of 5x minus 2 plus 0. That is nothing but 2 minus 5x. Okay, now let us consider our last and final case, that is case 4. Case 4 has a general formula of the RHS of the general formula e to the power ax into v form, where e to the power ax is nothing but our case 1, and we can take any form, that is our case 2 or case 3, like I explained in the beginning. The general formula for our case 4 is f of d is equal to e to the power ax into g of x. Here g of x is v, which can take sin ax, cos ax or x raised to n as its values. Here pi is found using the general working methodology, that is using the general equation, that is 1 by f of d into e to the power ax into g of x. Here e to the power ax is not considered for any calculation and is kept aside. And f of d, we make a substitution, d is equal to d plus a, and then we go about with g of x like how we learned in case 2 or case 3. Okay, now let us consider our example for case 4. The given equation is of the form d square y by dx square minus 6 dy by dx plus 13y is equal to 8 e to the power 3x into sin 5x plus 2 to the power x. Let's first convert the LHS of the given equation into a known form using the derivative operator, that is d square minus 6d plus 13 into y is equal to 8 into e to the power 3x into sin 5x plus 2 to the power x. From this equation, let us first find the CF for this given equation. That is, we have to first find the auxiliary equation. Auxiliary equation is nothing but when we substitute m is equal to d in f of d. That is m square minus 6m plus 13 is equal to 0, and we find the zeros for this given equation. And the zeros which we obtain using the quadratic formula for finding zeros are 3 plus or minus 2y. Therefore, from this 0, we know that the CF is nothing but y is equal to e to the power 3x into c1 cos 2x plus c2 sin 2x. Now let us come to our main part, that is finding particular integral. Particular integral here can be found using our general formula for finding particular integral, that is 1 by f of d into e to the power ax into g of x. Now writing our given equation in that form, we know 1 by d square minus 6d plus 13 into 8 into e to the power 3 raised to x into sin 4x plus 2 to the power x gives us our pi. This we have to separate into two parts. Part 1, which is a which is case 4, and part 2, which is case 1. We manipulate our 2 raised to x into the form e to the power 2 log x, that is 2 raised to x is written as e log 2 whole raised to e log 2 raised to x, which can be written as e to the power x into log 2. Now considering part 1 and part 2. 1 by d square minus 6d plus 13 into 8 e to the power 3x plus sine 4x is our part 1. Here e to the power ax, from e to the power ax we can find out a is equal to 3, and here we know that v is equal to sine 4x. Therefore here we have to proceed using case 2. 8 e to the power 3x is taken out here, and we are only considering our 1 by f of d and sine 4x, that 1 by f of d and v, that is 1 by d square minus 6d plus 13 and sine 4x. Here d is substituted with d plus a, that is nothing but d plus 3, 1 by d plus 3 whole square minus 6 into d plus 3 plus 13 into sine 4x. On simplifying this term, we get d square plus 4. And then from there we proceed with our case 2 method, where d square is equal to nothing but minus of a square, that is nothing but minus of 16. Substituting minus of 16 in this equation, we get minus of 16 plus 4, nothing but minus 12. And further simplification of this gives us minus 2 by 3 into e to the power 3x into sine 4x. Now let us go to our part 2. Here part 2 is nothing but an example of our case 1, that is e raised to ax form. RHS is e raised to ax form, that is logarithm function. Therefore here 1 by d square minus 6d plus 13 into e to the power log 2x, that is 1 by f of d into e to the power ax gives us our pi. Substituting a is equal to log 2 in our f of d, we get log 2 whole square minus 6 log 2 plus 13 into 2 to the power x as our pi for the second part. Therefore our pi is nothing but the summation of part 1 and part 2, that is minus 2 by 3 into e to the power 3x into sine 4x plus part 2, that is 1 by log 2 whole square minus 6 log 2 plus 13 into 2x. Therefore our solution for this differential equation is y is equal to the summation of our CF and PA, that is y is equal to e to the power 3x into c1 cos 2x plus c2 sin 2x minus 2 by 3 e to the power sin x into sin 4x plus 2 to the power x divided by log 2 square minus 6 log 2 plus 13, and hence we derive our answer.